Good morning, good afternoon, good evening, wherever you are. Let's learn robotics. This is the first lecture in robotics, and I'm your professor Atif Fareed Muhammad. So, the introduction to robotics starts with mechanics and control, where introduction, trigonometry, and spot robot, and the rest you can read by yourself. And let me go through a little bit of my understanding that I have established while studying robotics. Mechanics and control are crucial fields in physics and engineering that deal with the motion of objects and how to influence that motion. Mechanics is the branch of physics that focuses on behavior of physical bodies when subjected to force or displacements. It involves understanding concepts like force, momentum, and energy. Control, on the other hand, is an engineering discipline that deals with the behavior of dynamic systems. It involves designing systems that can control the behavior of other systems, often using feedback loops to adjust and maintain desired outcomes. The importance of trigonometry in mechanical and control fields, it's significant. The trigonometry plays a vital role in mechanics and control as it helps in analyzing and solving problems that involves angles and distances. In mechanics, trigonometry is used to break down force into their components, making it easier to understand how an object moves under the influence of multiple forces. For instance, when a ball is thrown at an angle, trigonometry helps in calculating the range and the height of the throw. In control systems, trigonometry is essential for understanding and controlling the movements of robotic arms, vehicles, and other mechanical systems that involve rotational motion. The principles of mechanics are fundamental to the field of robotics. Robots are designed to move and interact with their environment, which requires a deep understanding of how forces and motion work. Mechanics helps in calculating the torque needed to move a robotic's arm and force required to lift an object, or the trajectory a robot should follow to reach a specific point. Additionally, mechanics is crucial for designing stable and efficient robots that can withstand various forces and perform tasks accurately. Hopefully, this is helping you to understand how mechanics and control work in robotics. Let's explore a little bit more. Before I jump into the sales of robots in North America in millions of US dollars, let me finish a little bit about Spot robot that actually we will be discussing in this a little bit in more depth. The Spot robot, as mentioned on the previous slide, developed by Boston Dynamics, is an excellent example of the application of mechanics and control in robotics. Spot is a quadruple robot designed to navigate complex terrains and perform various tasks autonomously. The mechanics involved in Spot's design include calculating the forces needing to lift each leg, maintaining balance, and determining the optimal gait for different surfaces. The control systems in Spot use advanced algorithms and sensors to process environmental data, plan movements, and adjust actions in real time. This combination of mechanics and control permit Spot to perform tasks like inspecting industrial sites, assisting in search and rescue missions, and even dancing to music, showcasing the remarkable capabilities of modern robotics. Now, let's see why sales matter. According to the Robotics Industries Association, the sales of industrial robots in North America have been steadily increasing over the years, reaching several billions of US dollars annually. This growth trend reflects the rising adoption of automation technologies across various industries, including automotive, electronic, and manufacturing. The sales figures highlight the increasing demand for robotics solutions that can enhance productivity, improve product quality, and reduce operational costs. Why this matters, or why the sales matters even. The growing sales of industrial robots in North America are significant for several reasons. Firstly, it indicates a shift toward advanced manufacturing practices where robots play a crucial role in streamlining production processes and increase efficiency. Secondly, the increased use of robots can lead to job creation in areas such as robot maintenance, programming, and data analysis, while also addressing labor shortages in certain sectors. Additionally, the adoption of industrial robots can enhance competitiveness in the global market by enabling companies to produce goods more quickly at a lower cost. This trend also underscores the importance of investing in education and workforce development to ensure that workers have skills needed to operate and maintain these advanced technologies. So, now you know. Yearly installations of many multi-purpose industrial robots source World Robotics 2016. You might be thinking why I'm sharing 2016 data. The data in robotics needs a decade overview before we jump into any such thing to understand in more depth. According to the World Robotics 2016 report, the yearly installation of multi-purpose industrial robots have been on the rise globally. These robots, designed to perform a variety of tasks, are being increasingly adopted across different industries. The report highlights a significant growth trend, with thousands of new robots being installed annually in manufacturing plants, warehouses, and other industrial settings. This upgrade trajectory reflects the growing recognition of the versatility and efficiency that multi-purpose robots bring to various operations. Why this matters. The increasing yearly installation of multi-purpose industrial robots are significant for several reasons. Firstly, these robots enhance operational flexibility, permitting companies to adapt quickly to changing market demands and production requirements. Secondly, they improve productivity and efficiency by automating repetitive tasks, reducing errors, and increasing output. Additionally, the adoption of multi-purpose robots can lead to cost savings by minimizing downtime and optimizing resource use. Furthermore, this trend highlights the importance of technological advancements in driving industrial innovation and maintaining competitiveness in global market. Investing in multi-purpose robots are also necessitating upskilling the workforce, ensuring that employees are equipped to handle the benefits from these advanced technologies. So the labor cost savings from adoption of industrial robots, and you can see South Korea, Japan, Canada, United States, up to the Czech Republic, how this has been in certain impactful state. According to the estimates by the Boston Consulting Group, the adoption of industrial robots is projected to result in significant labor cost savings by the year 2025, which is yet to come, as the video has been recorded of this lecture. The report suggests that these savings could amount to a substantial percentage of current labor costs. The forecast underscores the potential of automation to streamline operations, reduce the need of manual labor in repetitive tasks, and enhance overall operational efficiency. Why does this matter? The projected labor cost savings from the adoption of industrial robots are significant for several reasons. Firstly, these savings can lead to improved profitability for businesses, permitting them to reinvest in growth and innovation. Secondly, automation can help address labor shortages and reduce the dependencies on manual labor, which is particularly relevant in industries facing workforce challenges. Additionally, the cost savings can make companies more competitive in the global market by enabling them to produce goods more efficiently and at lower costs. However, it is also crucial to consider that social and economic implications, such as the need of workforce retraining and potential impact on employment. Balancing these factors will be essential for a substantial and sustainable and equitable transition to a more automated future. A modern 7 degree of freedom or DOF robot. A modern 7 degree of freedom, as mentioned in the title here, the robot is a sophisticated piece of machinery designed to mimic the complex movements of a human arm. The term degree of freedom refers to the number of independent ways a robotic arm can move, with each degree corresponding to a specific axis of rotation or translation. A 7DOF robot typically includes 7 joints that permit for intricate and flexible movements, enabling a robot to perform a wide range of tasks with precision and dexterity. These robots are often used in industrial settings such as manufacturing, healthcare, and research, where their ability to maneuver in complex environments is highly valued. In 2008, I came into contact with the research that was conducted by Queen's University of Kingston, Ontario, and State University of New York at Buffalo, by merging their R&D to create a robot that could have been assisting a physiotherapist. And we actually experienced that firsthand at Queen's University in Kingston, Ontario, Canada. So 7DOF robot is not yesterday's story. The R&D is happening for quite a while, and I have witnessed that in person by myself. The mechanics and control of mechanical manipulators, constantly concerned with locations of objects in three-dimensional space. Frame can serve as a reference system within which to express the position and orientation of a body. Coordinate systems or frames are attached to the manipulator and the objects in the environment. Let's learn with an example. In a manufacturing setting, a 7DOF robot can be used to pick and place operations, where the robot is tasked with picking an object up from one location and placing that object in another location. To accomplish this, the robot's control system uses multiple coordinate system or frames. The base frame is attached to the robot's stationary base, providing a reference point for all movements. The end effector frame is attached to the robot's gripper, permitting the control system to track and guide its movements precisely. Additionally, an object frame is defined for the target object, enabling the robot to accurately calculate its position and orientation. Using these frames, the robot can plan and execute a trajectory to approach the object, grasp it, and move it to the desired location, even if the object is in a confined or hard to reach space. next example we can understand as welding in an automotive industry. That's in Detroit, perhaps Ford or GM or Toyota. In the automotive industry, 7DOF robots are employed for welding tasks where their flexibility and precision are crucial. To perform welding operations, several frames are used. The base frame serves as the reference point, while the end effector frame is attached to the welding tool, permitting the robot to control the tool's position and orientation accurately. A workpiece frame is defined for the car body or component being welded, enabling the robot to follow the complex contours and surfaces of the part. Additionally, a tool frame may be used to monitor the welding tool's status and ensure it is functioning correctly. By utilizing these frames, the robot can execute welding paths that require intricate movements and maintain consistent weld quality, even the challenging the tight spaces. So another example can be surgical assistance in the healthcare domain. In the healthcare, 7DOF robots can assist in surgical procedures, providing enhanced precision and control. For surgical applications, multiple frames are employed to ensure accurate and safe movements. The base frame is attached to the robot's stationary base, as mentioned earlier, while the end effector frame is attached to the surgical instrument, permitting the robot to guide the tool with high precision. A patient's frame is defined based on the medical imaging data, enabling the robot to navigate the patient's anatomy accurately. Additionally, a tooltip frame may be used to track the exact position of the surgical instrument's tip, ensuring that it follows the planned trajectory during the procedure. By utilizing these frames, the robot can assist surgeons in performing minimally invasive surgeries, reducing the risk of tissue damage and improving patient outcomes. Furthermore, the robot's flexibility allows it to adapt to the unique anatomy of each patient, providing personalized and precise surgical assistance if the patient comes back, for example. Importance of coordinate system or frames is crucial for the effective operations of 7DOF robots. These frames enable the robot's control system to track and guide the movements of the robotic arm and its end effector accurately. By defining frames for the base, end effector, and target objects, the robot can plan and execute complex trajectories, even in confined or challenging environments. The ability to transform and relate these frames to one another permit the robot to perform tasks with a high degree of precision and adaptability. There are some challenges. Managing multiple coordinate systems can be complex, as a robot must continuously track and update the relationship between different, and let me retrace my words. Managing multiple coordinate system X, Y, and Z, as a robot must continuously track and update the relationships between different frames. Challenges can arise from inaccuracies in frame definitions X, Y, and Z. Remember that. Sensor noise and dynamic changes in the environment. To address these challenges, robots often employ advanced algorithms for frame transformations, sensor fusion, and real-time motion planning. Additionally, techniques such as calibration, filtering, and the feedback control are used to minimize errors and ensure the robot's movements are accurate and reliable. By effectively managing coordinate systems, 7DOF robots can perform intricate and demanding tasks in the high degree of success. Hopefully, this has been helpful for you to understand the mechanics and control of mechanical manipulators. Again, kinematics is a science of motion that treats motion without regard to the forces which cause it. Manipulators consist of nearly rigid links which are connected by joints that allow relative motion of neighboring links. The number of degrees of freedom that a manipulator possesses is the number of independent position variables that would have to be specified in order to locate all parts of the mechanism. Kinematic equations describe the tool frame relative to the base frames as a function of the joint variables. So, as I discussed earlier, the challenges and solutions in coordinate system management, the kinematics is quite helpful in the aspect by creating the motion as and when required on the basis of the algorithms which are manipulating the hands or the robotic hands. Inverse kinematics, the problem is posed as follows. Given the position and orientation of end effector and the manipulator, calculate all possible sets of joints angles that could be used to attain this given position and orientation. For a given position and orientation of tool frame, values for the joint variables can be calculated via inverse kinematics. Let's look into this in more in terms of the set theory. Kinematics and inverse kinematics are essential concepts in robotics that deal with how robots move. Kinematics is about describing the movement of robot based on its joint angles, while inverse kinematics is about figuring out the joint angles needed to get the robot's end effector, like a hand or a tool, to a specific position and orientation. Kinematics can be forward kinematics or inverse kinematics. The forward kinematics is like asking, if I move my robot's joint this way, where will its hand end up? You start with the angles of the robot's joints and calculate where the end effector will be. For example, imagine a simple robot arm with two joints that can rotate. If you know the angles of these joints, you can figure out where the end of the arm will be. Whereas inverse kinematics is like asking, if I want my robot's hand to be at this specific spot, how should I move its joints? It is more complex because these might be multiple ways to position the joints to get the end effector to the desired spot, or it might not be possible at all if the spot is out of the robot's reach. Let's look at simple two joint robot arm. Think of a simple robot arm with two joints that can rotate. You can move these joints to different angles, and the end of the arm will be in different places. To solve the inverse kinematics problem, you need to figure out the angles of the joints that will get the end of the arm to a specific spot. This can be tricky because there might be more than one way to do it, or it might not be possible if the spot is too far away. Industrial robot with 6 joints, like those used in the factories, you have more joints to consider. You can calculate where the end effector will be based on the angles of all 6 joints. To figure out how to get the end effector to a specific position and orientation, you often need to use special methods or algorithms because it is too complex to solve with simple mathematics. Some robots have more joints than they need to reach a specific spot. These are called redundant robots. For example, a robot with 7 joints can have many different ways to position its joints to get the end effector to the same spot. To choose the best way, you might consider things like avoiding obstacles or keeping the robot in a comfortable position. In all these examples, understanding how the robot's joints affect its movement is crucial. By knowing the relationships between the joint angles and an end effector's position, you can control the robot to perform tasks accurately. And as I mentioned earlier, calculate all possible sets of joint angles. It's clearly mentioned here that set theory is very helpful in robotics because it provides a way to think about and organize all the possible movements and positions a robot can have. It allows us to group these possibilities into sets, making it easier to understand and solve complex problems related to the robot motion. Planning a safe path for a robot is a use case we can look into. Imagine you have a robot working in a warehouse and you want to plan a safe path for its move from one point to another without colliding with any obstacles. Set theory can help us break down this problem into manageable parts. So let's look into all possible paths in terms of set theory. Let's think here that all possible paths of the robot could take as a set. This set includes every conceivable route from starting point to the destination, regardless of whether they are safe or efficient. So what can be the safe paths? Next, we can create a subset of these paths that are safe. The subset includes only the paths that do not intersect with any known obstacle in the warehouse. By focusing on this subset, we can eliminate many dangerous paths from consideration. Efficient paths is the next level. Within the set of safe paths, we can create another subset of paths that are not only safe but also efficient. This subset might include paths that are shorter, faster, and use less energy than others. So now we can actually reach to the optimal paths. We can look for the best paths within the set of efficient paths. This might be the shortest path, the fastest path, or the path that uses the least amount of energy depending on what is most important for the task at hand. By using set theory to organize the possible paths in this way, we can simplify the problems of planning a safe and efficient route for the robot. We can focus on the most relevant paths and ignore the ones that are not suitable, making a problem more manageable and easier to solve. This approach can be applied to many different problems in robotics, from planning movements to avoiding collisions to optimizing tasks. Set theory helps us to structure and understand complex problems, making it a valuable tool in the field of robotics. In addition to dealing with static positioning, that's a problem technically, static position problem. We may wish to analyze manipulators in motion. In performing velocity analysis of a mechanism, it is convenient to define a matrix quantity called Jacobian of the manipulator. The geometrical relationship between joint rates and velocity of the end effector can be described in a matrix called the Jacobian. And you are looking at a pictorial representation which is quite clear about that. Let's move and see what we have more to learn in this lecture. So the example given, the gunner's job is to shoot the enemy aircraft. His gun is motioned in a mechanism that rotates about two axes, the motion being called azimuth and elevation. A World War I biplane with a pilot and a rear gunner, the rear gunner mechanism is subject to the problem of singular position. And you just see the screen how it moves. In order to accelerate a manipulator from rest, glide at a constant end effector velocity, and finally decelerate to a stop, a complex set of torque functions, as mentioned earlier, must be applied by the joint actuators. By reformulating the dynamic equations so that acceleration is computed as a function of actuator torque, it is possible to simulate how a manipulator would move under application of a set actuator torques. The relationship between the torques applied by the actuators and the resulting motion of the manipulator is embodied in the dynamic equations of motion. The pictorial representation is quite clear in this presentation here. A common way of causing manipulator to move from here to there is a smooth controlled fashion is to cause each joint to move as specified by a smooth function of time. In order to move the end effector through space from point A to point B, we must compute the trajectory for each joint to follow. Again, the set theory is also very much applicable in the calculation of this. Finite state automaton is another way in computer science that you can look at to calculate from state A to state B to state C to state D, and where the rotations are happening again and again in terms of a loop, and which one is the end state. The start state can also be the end state. Integral to the design of the manipulator are issues involving the choice and the location of actuators, transmission systems, and internal positions, and sometimes force sensors. The design of a mechanical manipulator must address issues of actuator choice, location, transmission system, structural stiffness, sensor location, and more. And this will permit you to look into further in the field of robotics in more depth. A primary concern of position control system is to automatically compensate for errors and to suppress disturbances. Position and velocity sensors are mentioned by the control algorithm, which computes torque commands for the actuators. In order to cause the manipulator to follow the desired trajectory, a position control system must be implemented, such as system uses feedback from joint sensors to keep the manipulator on course. The ability of a manipulator to control forces of contact when it touches parts, tools, or work surface seems to be of great importance in applying manipulators to many real-world tasks. In order for a manipulator to slide across a surface while applying a constant force, a hybrid position force control system must be used. Again, start state, some intermediate state, and a final state. This is finite state automaton, or finite automata is a base theory that is applicable here. Robot manipulators differentiate themselves from fixed automation by being flexible, which means programmable. Programming needs significant automaton implementation. That's why finite state automata, non-finite state automata, and the associated context-free grammar is very helpful for you to learn and understand in more depth. The desired motion of the manipulator and end effector, desired contact force, and complex manipulation strategies can be described in a robot programming language. Offline programming systems, generally providing a computer graphics interface, allow robots to be programmed without access to the robot itself during the programming. About Spot, Boston Dynamic robot. It has a hip, a back, mounting rail, a bottom, a knee, a foot, front, lower leg, upper leg, and all top. And you can see more in the given link, or you can go on bostondynamics.com. This is the example we will be using in these lectures in more depth. So you can see payload port X2, mounting rail x2. That is given for the mechanics and controls. Spot as a connected peer. Applications can be deployed on computers that physically connect to Spot via rear RJ45 port, the DB25 payload port, or RJ45 port on the Spot GXP payload, providing a reliable high rate communications link without infrastructure requirements but limits where the applications can be run. Spot as Wi-Fi access point, we can use that as well. Applications with physical proximity to Spot can connect to the Wi-Fi access point and communicate directly without any networking infrastructure. Spot as a Wi-Fi client. Spot can join an existing Wi-Fi network, and applications can also join the same Wi-Fi network to talk to Spot. This approach increases the possible range between application and Spot, but attention needs to be paid to dead zones in the network, handoff times between access points, and other considerations. Spot via custom communication links. Custom communication links such as cell modems and persistent systems radios can act as bridge between Spot and applications. These can be useful when the above cases are insufficient for network design. So again, this is the Boston Dynamics that is using all these in given to work with Spot. Robot discovery. So I understand that it comes with a fixed IP address, DNS name, MDNS discovery, custom discovery mechanism. But let's look into this in terms of finite state automaton, that how computer scientists can understand the robot discovery by applying the FSA or FA, which is finite automaton, or theory of automata. A finite state automaton is a useful tool for controlling and understanding the behavior of a robot, especially one with many degrees of freedom, like 7DOF robot as discussed earlier. An FSA or finite state automaton helps break down complex tasks into manageable states, making it easier to program and control the robot. Here's how you can apply FSA to 7DOF robot with a start state, a final state, and the loops. First example is pick and place task. Start state is idle. The robot begins in an idle state waiting for a command. The second state is move the object. Upon receiving the command, a robot transitions to a state where it moves towards the object to be picked up. The next state is third state, grasp the object. That's a command also. Once near the object, the robot enters a state where it grasps the object using its under end effector. Next is move to destination. After grasping the object, a robot transitions to a state where it moves toward the destination where the object needs to be placed. Next is release the object. Upon reaching the destination, the robot enters a state where it releases the object, and the last state is return to idle. It comes back. Finally, the robot returns to the idle state, ready for the next command. There can be loops associated. If the robot drops the object or fails to grasp it, it can loop back to the move to object state and attempts to task again. Additionally, if there are multiple objects to be moved, the robot can loop through the move to object, grasp object, move to destination, or release object state for each object before returning to the idle state. Next is welding task. Start state where the robot is in the idle state. The next state is move to weld point. The robot transitions to a state where it moves to the first weld point, perform weld. Once the weld point, the robot enters a state where it performs the welding operation. Move to the next weld point. That's the next state we are discussing. After completing the weld state, The robot moves to the next weld point. In the final state would be idle again. After completing all welds, the robot returns to the idle state. Okay, the last example I would like to share with you is an assembly task. Again, our start state is idle, the robot is in the idle state. The command comes pick up part. The state changes, state transitions. The robot transitions into state where it picks up the first part of the assembly. Next is move to the assembly point. With the part and its gripper, the robot moves to the assembly point. The next state is assemble part. The robot enters the state where it assembles the part onto the product being built. The next state is pick up next part. After assembling the part, the robot moves to pick up the next part. Last, not least, final state, after assembling all parts, the robot returns to the idle state. And the loops can be through pick up part, move to assembly point, and assemble part. States until all the parts have been assembled. If the part is not successfully assembled, the robot can loop back to the assembled part state and retry the operation again. In each of these examples, the finite state automaton helps to structure the robot's tasks into clear, manageable states. The loops allow a robot to handle repetitive tasks and recover from failures, making the system more robust and flexible. This approach simplifies the programming and control of the 7DOF robot, enabling it to perform complex tasks efficiently. And all these states, we need fixed IP addresses. This approach can be used reliably when connecting directly to a spot as a Wi-Fi access point or over Ethernet. No name lookup infrastructure is required. DNS or destination server. DNS server or host file can be configured to statically point to a fixed IP address that Spot listens to, and application specifies the DNS name and the reach, and the rest you can read. So about Spot, base and robot services. The robot ID service provides metadata about Spot robot. The auth service is used to authenticate a user to Spot. The directory service is used to discover which services are currently running on Spot. The time sync service is used to estimate the offset between the application's clock and Spot's clock. The lease service provides methods to achieve ownership over controlling the robot and maintaining valid communication with the owner. Robot services, there are different state services available on Spot are robot state service, as I mentioned earlier, image service, local grid service, world object service. Once fully in control, the client will need to maintain the software stop, enable motor power, and send commands. E-stop service provides a secondary keep alive mechanism by acting as a software stop. Power service, the power service allows a client power the motors and on and off. Robot command service, the robot command service allows a client to move the robot. Trigonometric identities, formulas for rotation about principal axis by the theta. See justification on the next slide. However, I would suggest you look into these matrices very carefully, that how our x, our y, and our z actually behave when we apply the cos or sine thetas on top of it. So again, the trigonometric identities, I would suggest you to look into this and try to understand and establish an idea that how cosine and sine thetas are applied, and what are the trigonometric functions which are used in this from idle state to the final state in terms of transitions, and that's where these formula are applicable. So the trigonometric identities example around Z2D example, and that's where you can look at PXY and PX hat and y hat, and how the movement can happen in y and y hat area in the two-dimensional frame that we are looking at this moment on the screen. So this is coming from your grade 12, grade 11 and 12 trigonometry understanding. Spot robot introduction, geometry and frames. X, Y, and Z, roll, yaw, pitch. Why these are important? Let's look into that together. The spot robot introduction, geometry and frames. OROM frame, an inertial frame that estimates the fixed location in the world, or 0, 0, 0, relative to where the robot is booted up, using the kinematics of the robot. Vision frame, an inertial frame that estimates the fixed location in the world from where the spot or the robot is looking to or looking forward to, relative to where the robot is booted up, and is calculated using visual analysis of the world and the robot's odometry. Body frame, a frame describing the robot's body position and orientation. The frame's origin is at a geometric center of the hip, and the x-axis pointing frame from hip center to the middle of the front hips, as shown in the illustration given in the earlier slide. Flat body GPE, fiducial XXX, filtered fiducial XXS, front left fish high. I would suggest you to look at these terms very carefully, because this will allow you to establish an idea that how geometry and frames are helpful for any given robot. Spot is an example here. The e-stop service uses the heartbeat-based software-implemented service to help guarantee a communication link between one or more off-robot host mechanics or machines. Client can be set one of the following stop levels: cut, actuator power is cut immediately, settle then cut, the robot attempts to come to a stop, sit down, and then cut, actuator power, none, no stop level, actuators are allowed to power on, this does not turn the actuators on. The e-stop service will allow actuators to be powered as long as the following conditions are met. There is a valid configuration. All endpoints in the configuration have been registered. All registered endpoints have checked in with the non-stop level. The number of seconds between each endpoint's previous check-in and now is less than each endpoint's timeout. The basic lease usage. Services which command and control the robot requires a lease. These services will reject incoming requests which are from non-owner or contain older ownership information. Ownership semantics provide additional safety to operation workflows by preventing accidental commands from disturbing the current owner's application. Understanding lease errors. When the command is sent including a lease, the service checks the following things before accepting the command. The incoming lease is valid, contains the current epoch, has known robot resources, and the resources are correct for this type of command. Has a non-empty sequence with a root lease number which has been issued by the lease service. The incoming lease shows ownership as the newest lease. Compares the incoming lease with the service's current known lease. So again, spot robot introduction to the lease service. The body has full arm and mobility, whereas full arm has gripper and an arm. The different robot resources created tree-structured hierarchies, such as the client can control a subset of the robot or entire robot without needing to manage individual resources. We have discussed the set theory with subsets and the implementation of the information that is given in a subset, how to utilize its right path, wrong path, or the least resistance path and all that jazz. And finite state automaton also applies. the state from idle to the final state with all the states mentioned earlier in our discussion. The interface developed services are expected to comply with the same service interface standards that all Spot services use. And I would suggest you to look into this in the given text at the gRPC and the gRPC documentation, which are available in the Boston Dynamics. So this will give you a more understanding how these services work. So consider this a little of your reading after this lecture by going on Boston Dynamics websites. Fault is grouped independently and can be accessed through the robot state. System faults, behavioral faults, service faults. The system faults indicate a hardware or software fault on the robot. They include an error, code, and message, and can inform a user about anything from perception fault with a certain camera to a battery overheating. Whereas behavior faults track faults related to the behavior commands and issue warning if a certain behavior fault will prevent execution of subsequent commands. Behavior faults include an ID, a cause, and a clearable status. Service faults are the third-party payloads and services may encounter unexpected issues on hardware or software connected to Spot. External service faults are able to be reported on the Clear via the API fault service accessible through the fault client. In summary, the finite state automata are invaluable for controlling and programming complex robots like 7DOF robot. By breaking down tasks into distinct states, FSA simplifies the robot's behavior and make it easier to manage. Examples such as pick and place, welding, and assembly tasks demonstrate how finite state automaton can structure repetitive and complex operations. Loops within the FSA permit the robot to handle errors and repetitions efficiency, and as you see, we can also categorize the system faults, behavior faults, and service faults in terms of subsets or the union of all the faults that happen for us to figure out the fixation of these things. I hope you had a chance to learn in this lecture the introduction to robotics as a good start. Let's meet after 1 week with lecture 2. Happy learning.